The stability of a discrete time system can also be determined by analyzing the transfer function h of z. For this, let's go back to the formula of h of z, which has a numerator and a denominator which are polynomials of z with coefficients b and a respectively. Since the denominator is a polynomial in z of order n, the system has n poles, of which we assume that nr are real poles and nc are complex conjugate pole pairs. The characteristic polynomial d of z can then be written as a product with one factor for each real-valued pole pl and a factor for each complex conjugate pole pair, where the poles have absolute value rl and phase plus and minus omega l, which can be rewritten using Euler's formula. This way, h of z can be rewritten as a sum, where there is one summand for each real-valued pole and one summand for each complex conjugate pole pair. The values of al, bl, and cl can be obtained by solving partial fractions. The impulse response h of k of the system is obtained as a sum of the inverse z transforms of the individual terms. The inverse z transform of the term al divided by 1 minus pl times z inverse is equal to al times pl to the power of k times the unit step function, which we know is stable if the pole pl has a magnitude less than 1. For a summand corresponding to a complex conjugate pole pair, let's first assume for simplicity that bl is equal to 1 and cl is equal to minus rl times the cosine of omega l, for which we know that the inverse z transform, so the corresponding impulse response, is equal to rl to the power of k times the cosine of omega lk times the unit step function. So the corresponding impulse response h of k is stable if rl, the magnitude of the complex conjugate pole pair, is less than 1. This leads to the general stability condition: the system with transfer function h of z is bibow stable if and only if all poles of h of z lie within the unit circle.